Good day and welcome back for part 3 of our discussion of triple integrals in spherical coordinates. In this video we will investigate one additional example, which is asking us to find the volume of the solid that lies above the cone and below the surface whose equation is given here. In order to sketch this solid, we need to identify the two surfaces bounding it. The first one is maybe more easily recognizable as a cone. In terms of x squared plus y squared plus z squared equals z, we may need to go back to our experience with quadratic surfaces. And I think the easiest possible thing we can do is try to group together like terms. If we subtract z from both sides, note we could visualize this as being the equation of a sphere, just not one that's centered at the origin. But in order to figure out that new center and new radius, we would need to complete the square. That is, we'd like to figure out what constant value can we add to both sides so that we can write our equation as that of a sphere. Based upon this coefficient of z being a minus 1, this should be z minus 1/2 squared. And z minus 1/2 squared would be z squared minus z plus a quarter. And we don't get to just put the plus 1/4 on the left side for free. It also has to go on the right side. And when it goes on the right side, note 1/4 is 1/2 squared. And this is exactly what we're shooting for. We now recognize that we have the equation of a sphere, the radius is 1/2, and it's centered at 0, 0, 1/2. So let's go ahead and sketch this solid. So we're above the cone, and we're simultaneously lying below the sphere who's centered at 0, 0, 1/2, and radius 1/2. So roughly speaking, if we were to sketch the upper half of our sphere, it would look something along these lines. And if we get rid of a few extraneous lines, what we see looks roughly like an ice cream cone. And our goal in this case is to set up a triple integral that would allow us to calculate the volume of this ice cream cone. And in order to do so, I want to come up with a description in spherical coordinates. So let's think about the two equations that make this up. We have the cone, which is given by phi equals pi over 4. And then we have the sphere. And if I'd like to convert the equation of this sphere into spherical coordinates, note the left-hand side is rho squared, and the right-hand side is rho cosine phi. And if rho squared is equal to rho cosine phi, then rho would be equal to cosine phi. And this shows us everything that we really need in terms of describing this. That is, how do the rho values vary? How do the theta values vary? And how do the phi values vary? And let's start with maybe the two easier ones. The phi values will vary from 0 to pi over 4. We go all the way around the z-axis, so our theta values vary from 0 to 2 pi. The part that's more subtle is to think about how do the rho values vary. You can have your rho value as small as 0 if you're located at the origin. And then if you travel along a ray coming out from the origin until you hit that ice cream scoop, your rho value would vary from 0, the origin, up to cosine phi when you hit the scoop of ice cream. And this is the difference between our previous examples. The rho value is bounded above by a quantity that depends upon phi, which means when we set up our triple integral, the d rho must appear before the d phi. But before setting up that triple integral, let's just take a moment to visualize this in GeoGebra. We can hopefully very clearly see our ice cream cone. We have the cone and the sphere. We're looking at how our values for rho will vary from 0 at the origin up until you hit that ice cream scoop, so cosine phi. Then the question is, how do those phi values vary? And we can see that phi is going to vary from 0 all the way down to where we hit the cone, phi equals pi over 4. And hopefully that just gives you a slightly better illustration and some more intuition than the simple pictures we'd drawn previously. We are now ready to set up a triple integral calculating the volume of this ice cream cone. So if the solid is E, the volume would be the triple integral over E of 1. And in order to put this into spherical coordinates, the dv is going to come rho squared sine phi, and then we need our 3 variables of integration. And remember that rho depends upon phi, so rho is going to have to come before phi. So I'm going to put it in the standard ordering we've been using, d rho, d theta, d phi. Rho on the inside from 0 to cosine phi. Theta in the middle varies from 0 to 2 pi. And phi on the outside varies from 0 to pi over 4. And this triple integral represents the volume of the desired solid. And at this point, I will leave the evaluation of this triple integral to you for good practice, but I'll note you can find this exact problem worked out as an example in the textbook. So if you have questions, do not hesitate to contact me. We will continue this discussion of triple integrals in general in our next video. So stay tuned and take care.